Last time we were starting to look at an entity relationship model. We said that the entity relationship model is the start of coming up with what is known as a relational database. So, the entity relationship model is required as a beginning, at the beginning, to be able to identify what are the entities will take part in the relation and what relationships they have with other entities. So, we said that there is no real algorithm to detect the identities, that is identify entities or the relationships. So, given a requirement specification or reward statement, one thumb rule is to pick up the nouns as entities and the verbs, the connecting verbs, as the relationship. So, in the case of student attend courses, then students is a name, there is an entity, and attend, which connects students with courses, is a relationship, and courses is another entity. Teacher, if teacher teaches courses, then teachers as one entity and courses another entity. They are related by a relationship called teach. Okay. And this is shown in a diagram where the squares, rectangles are used for entities, and rhombus kind of this diamond shaped box is used to identify relationships. Now, I looked at another example where if you look at orders, orders are placed for items and they are placed with vendors. So, the point of this example is to show that the same two entities may be connected by more than one relationship. In this case, placed for is one relationship and placed with is another relationship. So, the order has got certain attributes. The attributes is order number and order date. Order number, we said, is an attribute which identifies or uniquely identifies the order, and it is a key attribute. So, it has got to be unique. If you look at placed for, it connects with items. So, the item itself has got attributes, item code and item name, and the placed for has got a composite key, namely order number and item code. The reason is an order can be placed for many items, and the items may be in many orders, and similarly an order may be placed with many vendors. A vendor may have many orders. So, in the case of the relationship which is placed for, the order number, vendor code and item code, all three appear as a composite key. I will explain this in a greater length with more examples as we proceed, but the general idea is that before I really define what is known as the cardinality of a relationship, I am just giving this example, but cardinality or the so called is it a 1:n relationship or a n:m relationship, all those things will be the one which determines whether more than one key appears in the relationship or just a single key appears in the relationship. This the dependency and dependency diagram and so on will be later on, we will explain that, and then we will kind of understand this reason why more than one key is put in the relationship be evident because it's a composite, what is called a composite key. This is what meant by relation cardinality. We said that vendor can supply many items. Okay. If I look at the vendor and items are the entities, and supplies is a relationship which connects vendors and items. So one vendor number 1 can supply item 1 as well as item 3 in this case. So 2 lines are shown, and connecting V1 and I1 and V1 and I3, and when they cross that supplies relationship, a thick dot is shown showing that supplies connects these 2 entities. If we look at vendor 2 supplies item I1 as well as item, you can see he supplies item I2. So the item 1 is supplied by both vendor 1 and vendor 2. That means an item can be supplied by more than one vendor, okay, and a vendor can supply more than one item. Okay, this is called a multiple relationship. There is N is to M relationship, and this can be found out by just looking at this diagram and see how many entities are connected to how many other entities through the relationship. Okay, and from this diagram itself it will be very evident whether it is what is the multiplicity of the relationship. So an entity may appear in only one relationship, or in a fixed number of relationships, or in a variable number of relationships. In this case, with the simple example of just 5 items, the maximum vendor 1 can supply is 3 items. In fact, the maximum any vendor can supply is 3 items, because vendor 2 supplies 2 items, vendor 3 supplies 3 items. But the point is, if in general there are n vendors and m items. So if you don't have any prior knowledge of how many items a particular vendor can supply, it is indefinite, then it is called n to m. That is, observe the vendor can supply many items, and of course that many vendors can also supply the same item. So this is essentially the fact. So if the vendor supplies item can be represented by the entity relationship diagram, where I have shown n and m in the links between vendor and supplies and items. What it really means is that n and m are variable. So the number of vendors who supply a number of items can be variable. Similarly, an item can be supplied by many vendors, and that many is not defined by an actual number. Okay, it is a variable. It's arbitrary. It can vary from situation to situation. Another example on the right, where vendors against vendor supplies that arc, I put a value n, and between supplies and items in that arc I put a number 6. It means a vendor cannot supply more than 6 items. Okay, but n vendors can supply a given item. So when n is shown against vendor, it means number of items can be supplied, which a number of vendors who can supply a given item is indefinite. But as far as vendor is concerned, he is not allowed to supply more than 6 items. The third example here is that item can be, I put 2 against vendor and supplies in that arc, and an m in the arc connecting supplies and items. What this really means is that item cannot be supplied by more than 2 vendors, but a vendor can supply any number of items, m items. That is, given an item, no vendor can supply, not more than 2 vendors can supply that specific item. But as far as a vendor is concerned, he can supply any number of items. Okay, it can be item cannot be supplied by more than 2 vendors, a given item. Okay, but vendor so this is in other words, many items the specification really is in terms of the cardinality, connecting vendor supplies and supplies items. Okay. In this case, another example, I put 1 and n. That means the teacher can advise n students. Okay, one teacher can advise n students, but a student cannot have more than one advisor. Okay, so this is what this relationship is. One teacher advises n students. Observe that in the advisors relationship, so in other words, when I look at the look at teacher is described by a teacher ID, name, department, address. Similarly, a student is student ID, name, department, address. The advisors has a key. Normally, if it is a 1 to n relationship, then the student is not part of the composite key, because given the teacher number, the student is known, because a teacher can in other words, for any given a student, your teacher is known. Okay, but given a teacher, a student, he can actually advise many students. So in that relationship, teacher and student must both appear, but as far as the key is concerned, it is teacher only, not a student. In fact, in this bold phase which is shown here is not really relevant. I have shown that just to indicate the possibility. Suppose there are a situation is changed, and you have something like 2 instead of 1 and n instead of n in down below. That means the student can have 2 advisors. Okay, and if the student can have 2 advisors, but the teacher can advise many students, then there is a requirement of composite relationship, because given a student, I cannot identify who is the teacher who advises, because more than one teacher advises the student. So teacher student, if they are given together as a composite key, then given the teacher number and student number, I can essentially find out the fact that the student has 2 different teachers who can advise him. The advising, of course, depends upon situation. There are situations where a student may have only one advisor in a certain year, say first year, but he may have multiple advisors in later years, depending upon the courses he takes or some other work he does. So the point is, a composite key becomes relevant when there is a multiple relationship, multi-order relationships, or cardinality is multiple. If in the previous case, I assumed that every teacher is expected to advise 1 or more students, any number of students. You suppose there are certain teachers who don't advise at all, and any given teacher cannot advise more than 3 students. Then I put a little circle, open circle below teacher, which indicates that a teacher may not be required to teach to advise at all. That means that 1 is not compulsory. He doesn't have to, the teacher can be absent in certain advisors relationships. Okay, and whereas a student, every student must have an advisor. That is quite clear from this diagram. Okay, but then it also indicates that not more than 3 students can be advised by a given teacher. So that is this gives a cardinality in this case. The identifier of a relationship will be composite if the cardinality is n:m. It will be single if the cardinality is 1:m. If an entity has a circle attached to it, not all entities in the set may be present in the relationship, because some teachers in the previous case, some teachers do not appear in the advisors relationship. It will be this idea of cardinality will be useful in later on in what is known as normalizing databases. At this time, of course, it's a little bit you might say looks more theory than necessary, but I think this theory becomes a groundwork later on when we talk about the idea of normalization, because idea of normalization comes based on the cardinality of relations. Okay. Entity sets and relationship sets are useful in designing databases. That is the reason we talked about entities and relationships. Entity and relationship sets may be put in a table of values. Okay. This is called a relation. A relation, see, there are a lot of mathematical definition of relation and so on, and the pure theory of relations as proposed by Card, the mathematical definition of relations have been used because there is something called relational calculus which he proposed, which has a number of operators, like say in differential calculus you have operators like differentiation, integration and so on. Similarly, relational calculus has got certain operations called project, join and so on. We will not really look at that in this particular set of short 3 lectures. Just to give you a broad overview of what relationship, what's a relation and how is a relation important in a database, and how is a database management system created using relations, because today almost all database management systems are relational database management systems. As I told, there are entire courses devoted to database management systems where the relational calculus and all the groundwork we will discuss in detail, but in this course on systems analysis and design, to the extent that we are expected to as a systems analyst understand what a relationship is, what a relation is and what is a relational database, I think we are giving a bird's eye view of the theory of relational database. So, this will give you a very important kind of a grounding and also the motivation to go into the later course on database management systems, which is an important course in the computer science curriculum. Entity relationship set may be put in a table of values. As I said, this is called a relation. Relation name is an entity name. So, the name of a relation is one of the entities. A row of a relation is a member of an entity or a relationship set. Like let us take an example. If I take just a vendor which is an entity, vendor has got vendor is the entity name, okay, and the entity name has many attributes. So, the relation is a relation representing vendor and it has got many attributes. In this case, the attributes which are shown are the vendor code, because we need a unique identifier for a vendor, and the unique identifier is the vendor code, and there is a vendor name which may not be unique, need not be unique, and the address. The address normally is unique but need not be, maybe more than one vendor is sharing the same address. Okay, that is so that is, as far as we are concerned, irrelevant. So, the address is one of the attributes of the vendor. So, given the vendor code, I will be able to find out the vendor name and the vendor address. Okay. So, the relation is shown in a shorthand form as vendor as the relation name, and within parenthesis the attributes, namely the in this case the attributes are vendor code, vendor name and vendor address, and this row of a relation is called a tuple because it's got tuple, and generally when you say n tuple, that means there is you might say look at it as a vector with n components. So if you look at a row as a vector in a data structure point of view, it's got 3 components, in this case the 3 attributes. So row of relation is called a tuple. In the relational, row can be in any order. There are rows, there is no particular ordering of the rows which is imposed by the definition of a relation. Similarly, columns can be in any order. Okay, so this is also allowed. But normally, the unique identification of the relation, namely in this case vendor code, is normally put as the first attribute. Okay, and the others follow. So normally the first attribute is always the unique identifier, and the other attributes can be in any order. Okay, that's probably a better way of doing it practically. Okay, even though in theory they can be in any order. Okay, no 2 rows can be identical, because that means it's duplicated data. Okay, obvious. No 2 tuples can be identical. Then it's redundant. Okay, no 2 columns can be identical, because they are different attributes which describe the same entity. So you cannot have attributes actually duplicated. See, same attribute cannot be in more than one column. These are simple common sense reasons. Okay. So relation is the entire table, but we use a concise notation, as I said. Relation name and attributes. So relation name is vendor, and relation identifier is vendor code. That is, the identifier is essentially the key. Okay, I have been using the term key and identifier as synonymous, but normally the term identifier, relation identifier, is more accurate terminology to use. And the relation attributes. Some more example, if you take item code and item name is an entity, and relationship is supplies. Supplies, because the item code is connected to vendor code, and there is a multiple, there is cardinality is n to m. In the supplies relationship, both vendor code and item code appear as a composite identifier, and then the order number, quantity supplied, date of supply, and price per unit. Okay, there is a supplies relationship, because the vendor, the reason why the composite thing appears also is that the a vendor and item together only determine the order number and also the quantity supplied, date of supply, and price per unit, because by itself vendor or item will not have any of this. So if you look at the vendor relation, the vendor relation will have vendor code, vendor name, and vendor address, whereas the quantity supplied, order number, and so on is not there in either the item relation or the vendor relation. Supplies is the one which connects these two, and other attributes which are important as far as supply is concerned is put there. Another reason may be that because these vendor code and item code have appeared together, because price per unit may be dependent on the vendor. You may be giving different prices to different vendors for whatever reason. Maybe one vendor's quality is better. Okay, and obviously the quantity which is supplied will depend upon the vendor and item together. Okay, so that is the reason why the composite thing is required. Whereas in the case of a teacher advise a student, if multiple teachers are there for advising multiple students, then teacher ID and student ID will occur together in that basis. Otherwise, student ID is only an attribute and teacher ID is the identifier, because given the student ID, I can always find out which teacher advises that student. Okay, so the boldface are the key attributes. So why do we use relationships, relations in general? So relation, as we said, is nothing but a table, okay, and it is called a flat file in the computer storage. In other words, the computer storage, see, as far as the theory of database is concerned, we don't really look at the physical storage of that logical database. So now we are looking at the logical database design. The physical storage is based on whatever device you are going to use for storage, and the attributes of that physical storage change from time to time to time. Like for instance, today disks have certain characteristics. Few years from today, the characteristics of the disk may change. So mapping from the logical database to the physical device is device dependent and it will change. Whereas in the design, the logical part is going to become invariant. So the logical part is important, because once you come up with a logical design, then later on DBMS is more like a mapping, a method of mapping, you might say, and that mapping may change with time. I'll look at that later on in this course, this mapping idea, but this time we are more or less concerned about the logic of relationships. Sound theory of relations allows systematic design of relational database at the logical level. So there is a theory of normalizing relations. The question is, the normalizing relations is an important cornerstone or the foundation of the theory of relations, and that is very important from the point of view of logical design of databases. Why do you use a relation? When you use a relation, it reduces duplication of data. See, actually, when you talk about relation in general, you do it is a flat file, and flat file is something where, when you talk about a flat file, what it really means is that every record in the file has the same property in terms of length. So the records are all of equal length and they are all stored one after the other. If it is a sequential file, it will be in some sequential order of the key. If it is any kind of a direct access file, it may be just scattered all over a physical device. But the identifier, of course, anyhow is the key. And if it is scattered all over the disk, there is a key to address transformation which one can use, and given the key, you can always find the address of direct access storage device like a disk and access it. Okay. So once you access, you are accessing a fixed record size. That is what you mean by a flat file. Okay. And the use of relational database and this normalizing, which we will talk about, reduces duplication of data, tries to eliminate errors in adding, deleting, altering items in database. Because one of the most important things in a database is that no database is static. Because suppose you are looking at a database of students in a college. Students may leave the college in the middle of the term, or students may be joining the college year after year. Okay. Or students may be actually changing their address. Okay. So the addition and deletions are important in altering, like the address changes. I had to change the address, and I had to change the address at only one place and not at multiple places, because if I have to change the address in multiple places, there is always a possibility of error. So, eliminate errors in adding, deleting and altering databases. In fact, one of the most difficult or common problems which I encountered earlier was that when there is not sound theory of databases, this inconsistency always arose in a file based system, because there are multiple files and you update some file and don't update some other file, and you get into difficulty because the same student in different files may have different addresses. Okay. So, that is kind of a thing which you can want to completely eliminate in terms of a relational database. Simplify retrieval data. So, all this is done by what is known as normalizations, and we will have to first define what is normalization of relations, why do we normalize relations, and how are we going to normalize relations, because we start with what is normalization, then we describe why it is important, because very often students know how to normalize without understanding why we should normalize. Okay. And what is normalization is very straightforward. Normalizing is the process of restructuring relation to a form which minimizes duplication of data in a database. The reason why we normalize, the normalization is a process of restructuring which minimizes with the aim of minimizing duplication of data in database. Operation of adding, deleting, modifying data in database do not lead to inconsistent data in the database, and retrieval of data is simplified. Okay, this is essentially the point I made last time also. A collection of relations relevant for an application constitute a relational database, and relations are normalized to ensure that collection of relations do not unnecessarily hold duplicate data. Because duplicate data can be, if there are multiple relations and same data is repeated in multiple relations, then you will have an update problem. Whenever you update one relation, you should remember to update all the other relations where this data appears, otherwise you will have inconsistency. When a data item is modified, it is modified in all relations where it appears. No inconsistency is there. When data is deleted accidentally, required data is not deleted. Okay. That is, in fact, I should say that sometimes data is not deleted accidentally. When data is deleted, in fact, I should specify it much more correctly. When data is deleted, required data is not deleted accidentally. Now, the point is, when a particular data is deleted, some other data is not accidentally deleted. Okay. This is what is implied by this sentence. In fact, the sentence is not properly formed. When data is deleted, required data is not deleted accidentally, somewhere else. Okay. So, that is what we want to ensure. And we start with the process of normalization starts with an unnormalized relation. Like in this case, an order number, an order date is there, and the order is placed on number of items. And so multiple items, the order may contain more than one item. Okay. In this case, I have not really looked at who is going to supply the item. I am just looking at an unnormalized relation of order. What is an order? Okay. And in this case, the order is got a date and a certain number of items for which the order has been placed. And observe that the order has many items. So, if I look at it as a file, each record in the file has got variable lengths, because in some records, because order number and order date is common and item lines is variable. So, item lines being variable, some records may be long, some records may be short. So, it is a variable length file, which is always very difficult to handle in any practical situation. That is one problem. Okay, item lines have many attributes called composite attributes. Each tuple has a variable length, difficult to store due to non-uniformity. As I said, the record is a variable length record, and given item code is difficult to find quantity added. That is, given the item code, like in this case, you have to go through the entire relation from top to bottom. Like suppose 4627, I want to find out how many items of 4627 are ordered. Then second line it is 38, and then the fifth line it is 30, sixth line is 40. I have to add 40 plus 30 plus 38. So essentially, more or less, I have to search through all the entire all the lines, and effectively search through the entire file, you might say, before I can really find out how many items of a particular type has been ordered. So this is not a very satisfactory kind of a way of representing logically the data. Okay, so it's called unnormalized relation. So I cannot first, in fact, I should really start with something which is not normalized. In other words, it is not really a relation at all in the sense of the definition of a relation, because relation is a flat file. Okay, so I should change it. Identify composite attributes, convert all composite attributes to individual attributes, duplicate common attributes as many times as lines in composite attribute. Every attribute describes a single property, and no composite attribute should be present. In other words, the point is, if I look at this, there are a variable length. I should make all of the lengths equal, okay, by duplicating, okay, if necessary. Every attribute describes single property and no composite attributes. Some data may be duplicated. It is called first normal form, or called a flat file. In other words, any relation, I start with the first normal form. First normal form is the, you might say, zero state or beginning state. So I have taken the same one, and if I take this 1456, there are 3 items for each order number is 1456. So I duplicate that 1456 order date, item code, quantity, price per unit, and I am duplicating, and so I got a set of lines where each tuple has got a length of 1, 2, 3, 4, 5. So there are 5 tuple representing each line in the relation, and there are, in this case, a set of tuples. Okay, there are 3 plus 3, 6 tuples which represent this first normal form relation. The first normal form, as you can see, lots of duplication is there, and duplication creates a lot of problems. Okay, and so we normally, for instance, in this case, suppose order number 1456 is cancelled for item 3687. That is, I don't want to cancel 1456 completely, but only for the item 3687. Then I have to go through the entire file to match 1456 and 3687, and then only kind of delete that row. Okay. Otherwise, if I delete 1456, all 3 first lines will be deleted. Okay. Other items which I may still like to have in that order will be gone. Okay. So this is not a good idea. Or if suppose the price is changed for an item, I have got to go through all the item codes, and like with the 4627, the price is changed from 6020 to 5820, it reduces. Then I got to go through the entire n tuples, in this case all 6 n tuples, and then change wherever it appears, okay, which is not a very nice thing to do, okay, it is not a convenient thing to do, okay. I would like to have straightforward convenient ways of doing it, so that I don't have to do a lot of searching while doing any deletion, and not only that, I should not delete accidentally, okay. So normally you start with first normal form and you go to higher normal forms, second normal form, third normal form, and there is something called Backus, the Boyce card, not Backus. Backus is a person who actually invented Fortran. So there is a Boyce, another person called Boyce. Boyce card normal form, and there is a fourth normal form and fifth normal form. There are normal forms seem to be coming out all the time, okay. Some person finds out little problem with the with some normal form and then tries to come up with a slightly better situations in certain pathological cases, okay. And what I mean by pathological cases are cases which are rare, they don't occur all the time, okay, but still there is a theory which exists, and by and large I think in practice up to BCNF is quite satisfactory for most situations, but of course I shouldn't generalize, because after all researchers have gone to higher normal forms for good reasons, it is not trivial reasons, because they found some practical problems when dealing with relational databases. So in fact you may find that 5NF is not sufficient, and one may have to go to 6NF and God knows what NF, but I am going to start with 5NF, and in any case I am going to concentrate more on the up to BCNF, okay. First normal form is the first essential step, and each improvement is an improvement of preceding one, and higher normal form also satisfies the requirements of a lower normal form. Unless something is in first normal form, I can't start in fact and go on to second normal form. You might in fact this figure may be somewhat misleading, because 1NF is a much bigger set, and 2NF is a subset of 1NF, and 3NF is another subset of that, and 4NF is a further subset. In other words, in fact, if I want it in a set theoretic fashion of contained in, then I should really put first NF and then make everything else contained in that 1NF, okay. But here I am talking about requirements fulfilling. There is 5NF has to be 4NF, has to be BCNF, and has to be 1NF to begin with, okay. Higher normalization steps are based on detecting dependence between attributes, okay. Dependency is a very, very important point when it comes to normalization. So dependency between any attributes, any two attributes, there is no algorithm to find out dependency. Dependency is to be found out by common sense, or the sense of the problem, the statement of the problem, what the dependency really means. And so the process of normalization is not entirely algorithmic. What I mean by that is, it is not possible, given the requirement specification as a work statement, to have a computer program create a normalized database for you without any human intervention. That is very nice if it happens, but then if it happens, it will put a lot of us out of business. See, after all, when you learn all these things, a human brain and the use of our language ideas and the idea of common relationships and so on are the ones which are useful in describing the normalization. And so, the entire normalization process is more of a manual process, and that is the reason why it is both challenging and also error prone. Challenging because you have to make it in such a way, or you normalize in such a way that no errors creep in, okay, and you have to understand the problem fairly well. So, good system analyst is able to normalize a relational database in a good way, so that no problem of what the inconsistency in updation and incorrect deletion or incorrect additions take place in the database. So, normalization is based on detecting dependence between attributes, identifying what are the key attributes, detecting multi-value dependency between attributes. Now, in fact, we found out that there is something called a relation cardinality. So, between relations there are multi-valued connections. Like I said, multiple teachers can be teaching multiple courses. That is, one teacher may teach many courses, and one course may be taught by many teachers. In some places there are multiple sections of a course. The same course may be taught by more than one teacher. Okay, so there is a multi-valued dependency. But on the other hand, if one course can be taught by only one teacher, then of course it is a single value dependency. Well, given the value of teacher, I know given the course, I know which teacher teaches it. Okay, and but a teacher may teach many courses. See, so this is a kind of what is meant by dependency. Given x and y as two attributes in relation, and for each value of x, only one value of y is a corresponding value, then you say it's a y is functionally dependent on x. That is, in other words, given x, you can find out y. It is like saying y equal to fx. Okay, what does y equal to fx mean? Given the value of x and given the function, you can calculate f of x and find out y. So, y is dependent on x. So, it is somewhat similar to that. Given the item code, item name is known. Okay, and so this is called a dependence. See, the name depends upon the code. Therefore, item code is functionally dependent on item. In other words, given x, what value of y correspond to it, y is functionally dependent. So, that means item name and item code are functionally dependent, and functional dependence may be based on composite attributes. Okay, odd number and item code together, namely composite attribute, had to be given to find out the quantity ordered and the price. So, in other words, the dependency may be dependency based on composite attribute or a single attribute. Based on a single key, one type of relationship, but based on composite key, a different type of relationship. This distinction becomes important in the normalization as we look in future. So, normally dependence is shown, it is what is known as a dependency diagram. So, you got in fact diagrams are very nice to have, because as a picture it gives you a lot more intuitive understanding. So, in this case I have given a student relation, and the student relation has got a identifier or a key which is roll number, and a roll number, given the roll number, there are number of attributes like name, address, department, year of study, they are all functionally dependent on the roll number. Okay. So, roll number is therefore a key. In other words, given roll number I can always find out the name, address, department, area study. So, roll number is all the others they are functionally dependent. Roll number and name are functionally dependent. Okay. And given the roll number I can always find out the name. Okay. Composite key is enclosed in one box in the dependency diagram. So, in this case I got vendor code and item code together. It is a composite attribute, and the lines show that quantity supplied, data supplied and price per unit depend upon the both vendor code and item code taken together. Okay. So, composite attributes always enclosed in a box, and in this by implication it means that the none of the quantity supplied, data supply or price per unit is dependent directly on item code alone or vendor code alone. Okay. And both have to be vendor code and item code have to be given together as a composite key in order to find out the other the quantity supplied, data supply and price per unit are dependent on the composite attribute vendor code and item code. Why normalized relation? I think revisit it. In other words, I am repeating what I said earlier to ensure that while operating on database we do not lose data, we introduce inconsistencies while doing any kind of an operation on database. Operation on database or insertion of new data should not force leaving blank fields for some attributes. In other words, if I enter a new data item, see by definition a relation has got attributes and every attribute has got a value. So, I should not get to a situation where some attribute values are blank. Deletion of a tuple should not delete vital information, obviously. I mean, some vital information should not be lost while deleting some item. Updating or changing value of an attribute should be possible without exhaustively searching all tuples. We saw that earlier, that is if I don't, in the first normal form I have a problem. See, insertion, enter new item code. Suppose you want to, in the first normal form, enter or insert a new item code with the price of 30 rupees 50 paisa, for which no order has yet been placed. Then you may have negotiated a certain price for an item with a vendor or more than one vendor, but you have not yet placed the order. If you insert that item with code 39445 and price 3050, there won't be any entry for quantity and there won't be any entry for order date, okay, and there won't be any entry for order number. So, there is obviously a situation which is not acceptable. And if you delete order number 1886 to be deleted, the fact that item code 469 cost 2025 is lost. In other words, if I look at 1886 here, 1886 if I delete, 1886 occurs at two places. So, I repeat, if I take out 1886, the fact that 4629, the item code 4629, see I can just look at that, 4629, see, cost 2025 will be lost because I am deleting 1886 and also I am deleting this, but fortunately 4627 is occurred somewhere else, and so this is not deleted, but this 2025 gets deleted and that information is not found anywhere else. Okay. The price item 4627 is changed. In fact, I told you earlier, you have to look at all things of the item code, how it is changed. So, I'll kind of look at all 4, 6, 2, 7s occurring, exhaustively search the entire 1NF relation to be able to find out all the rows where I have to change, and without without leaving out any by accident, I should essentially change all of them, otherwise there will be an inconsistency. Somewhere the price will be 60 rupees, 20 paisa still old price, and somewhere the price will be new price. So it will be inconsistent database. At the end of normalization, an ideal normalization is 1. At the end of the normalization, should have no data values duplicated in rows. In this case, I got duplicate data values now, like 1456 gets duplicated so many times. Every attribute in a row must have a value. Okay, no blanks are allowed. Deletion of a row must not lead to accidental loss of information. See, deletion in this case, I showed the example of deleting one particular order, then the price is lost. Okay, so deletion must not lead to accidental loss. At the end of normalization, a normalized relation, adding a new row should not affect other rows. Okay, I should be able to add new rows, and a value of an attribute in a row can be changed independent of other rows. Okay, and so that is a normalized. In other words, the point really is you have to eliminate unnecessary searching, and you have to be clear, or you have to be certain that when I change something, only that gets changed, something else does not get changed. So the next step is to go from what is known as a 1NF to a 2NF. So we start with 1NF, and the non-key attributes are functionally dependent on key attribute. Okay, all non-key attributes must be functionally dependent on key attribute. By key composite, then no non-key attribute can functionally depend on one part of the key. So I will explain this in greater detail next time, because 2NF is a starting point for further details of 3NF and so on. So we should understand 2NF a little bit more clearly. I don't want to rush through it, and so I will stop at this point and continue from this next time.